All right, the last lecture we talked about the concept of pipeline, which means that we break up the logic of a single processor into several different stages, and each cycle we only make progress on the partial progress that we need to make for an instruction. And the good thing about this is that we can shorten the cycle time. And if everything goes smoothly, in theory, every cycle we can still generate the outcome for an instruction. So we are maintaining the same CPI, the same instruction count, but with a shorter cycle time. However, the goal of having a CPI equal to 1 is actually not that easy. So, and the reason of that is because we have 3 different types of hazards that prevent us to have a very smooth execution of the pipeline instructions. And these 3 type of hazards are structural hazards, means that our pipeline hardware design doesn't allow 2 concurrent instructions to access the same hardware at the same time, which prevent the concurrent execution of both. And the other one is called control hazard, meaning that there are cases where we don't know what's the next instruction to fetch. And if once you stop fetch, there is no way you can continuously generating outcome for an instruction because there's not really an instruction being input. So that's why the control hazards is also an issue that prevents us to get back-to-back output for instructions. And the other one, which is probably the most natural thing that people would come up with, is called data hazard. It means the case where a previous instruction is the source of the input of a later instruction. However, because it needs time to generate the outcome, so turns out, and propagate the outcome. So turns out the later instruction always have to wait. So these 3 types of hazards is preventing us from to get the pipeline performance better. And the solution is pretty much just stall, meaning that we force the later instruction to wait, or we can more aggressively improve the hardware design in a way. For example, for the reduced file, we can make it write first and read later. Or we can adopt a split L1 design, which you already see a lot in our assignments. So, we have been talking about structural hazard. And the other type of hazard, called control hazard, arises from the fact that we have branch instructions. So the concept of branch instruction is pretty much in our program. We do have the control flow, and where are the control flow? For example, every loop has a control flow because we need to check if we are within the condition to continue the loop. And every if-else statement is also implemented as branch instruction, and sometimes based on the outcome of the condition that being evaluated, it decides where is the next instruction to go. And there is a terminology called taken in branch. And the concept of taken, it just means that we are changing the target address to be the next PC instead of the instruction that goes forth through. And there is no rules regarding the syntax meaning of your the evaluation result and your and your branch is taken or not taken. So for example, if we take a look of this loop, this loop is basically checking the condition if I is equal to size, is smaller than size. And if I is smaller than size, and we should continue going inside this loop. So what turns out, as you can see, this L12 is the beginning of the loop, and this JL12 is the end of the loop. And what happened here is that based on this comparison, if it's less than, then we are going to continue in this loop. So in this case, we are taking the branch, which means that we are changing the direction from going forth through to backward if we found the evaluation result of this one to be true. So this is a case where we consider branch taken when it's true. However, if we take a look of the if statement here, so if you check the code like call when true, right? And how do we reach that call when true? It's actually just keep going on without any jumping, right? So if you think about what is branch taken means that we are going to jump to another address. But here, if you really want to reach call when true, you don't want to have any address jumping. So what does that mean is, this is the case where when the evaluation result is true, we are not going to take the branch. And we take the branch, which is the jump here, which would force us to go to the call when false, means that this is a branch when it's false, it's actually taken. So this is an example, true, taken. This is an example, false, taken. So you know there is no rule about a branch taken or not taken to be related to the evaluation result in your statements. So how do you tell this? So most of the time you can only check the assembly language, but in this class, just pay attention to the comments that I put beside each branch evaluation. That's the key. So now, so why is branch so problematic? And the answer is because without the next PC being determined, I cannot fetch the next instruction. And I have no idea what to fetch. And based on the pipeline, like the JNE instruction, depending on the compare instruction. So what I really need to wait is the end of the compare instruction. And without knowing the compare instruction, evaluate the statement that I'm curious about, I have no way to decide if I have to jump or not. And once I got that result, I can determine the effective branch address to go in the execution stage. However, it also means that the time you have to wait is almost as long as the latency of waiting the previous instruction go through the execution stage. So this is actually also another source of inefficiency. And later in this lecture, I will tell you why we do care about this latency. But the takeaway here, but the thing is that most of the time we just don't want to wait. So in our modern processor design, we always try to guess what will be the next instruction. So it will keep us fetching instructions that may potentially be executed. Because if we guess it right, then we can make forward progress without waiting. Even though we guess it wrong, as long as our hardware allow us to canceling those wrongly fetched instruction, wrongly executed instruction, then we will be fine. So that's why we have nothing to lose in branch prediction. And now, before we start the lecture today, I just want to ask you a question regarding, like, when you really need to make a guess, how do you typically make a guess? Grab a few people around you. So how do you guys typically guess? How do you guess? How do you guess during your midterm? How do you guys guess?
I use the context clues.
Context clues. Tell me more about it.
Well, I use the variables given, and then I use logic, such as using concepts from lecture,
Mm-hmm.
and then that's where I make my guess.
Okay, so you use some logic and based on what was previously being read in the test to guess the following, or you are saying about like eliminating or something like that. Okay, so like yeah, this is not possible, right? Okay, so least likely being eliminated. Other things, other thoughts? Just gamble, like do you what kind of gambling are you making?
I mean, I think the previous one was like assuming there's like someone like this one's likely to be wrong, and the other one's like so. One of our discussions like given like some probability, maybe this one's like a hunch, 20%, the other one's like 50%.
Oh, so you give confidence level to each.
Yeah.
Okay, that's a very wise strategy. Okay, what else? This is a machine learning question? Yeah, it could be. Like, okay, how can you make yourself guess like a machine learning model? Okay, look over the history in the past and okay, what kind of history are you looking?
Like if you have a similar question in the past that you saw, then like use similar wording or something. You remember the answer to that.
Okay, what else? If I completely have no idea about what the question is talking about, what do you think? You go with your heart. Okay, what else? Okay, so like for multiple choice questions, what are you guys going to do?
C.
C, okay, like the like why is C? Because based on like probability, there's always a C, right? What else? Okay, so the other way of looking at the probability. If you don't have to make a lot of guess, you're confident like, okay, the rest of questions, they are correct, right? And you don't see any question with an answer C, then what will you do? Just guess it as C, right? So because probability based and everyone should have the same equal occurrence, right? And if there's no like if C is very showing up very rarely, maybe I should give it more C. Okay, so these are all the ways that we can potentially guess. So today we are going to talk about how our processor guess what's happening next. And so first of all, we talk about control hazard, and the cost of not dealing with it is that we have to wait until we know the outcome, which is just a waste of time. So it turns out the last time we talked about the computer always make a guess, the processor always make a guess called branch predictor. So now my question is that, okay, we have branch predictor. Then what the branch predictor should guess for us? Oh, I think, yeah. So ignore the first sentence. This question should be asking what the branch predictor should predict. The first sentence seems like to be from an older question. All right, we got 6 of you answered. Means the next address. All right, let's take a look. Okay, we have B, C, D, and a lot of you guessed C. So why don't you guys just discuss, is it really C? All right, let's take a look. So after discussion, okay, there's no change. Okay, so some of you insist it's just one, some of you insist it's just there are two. Okay, so at least people agree there's one thing that we need to predict. What is that? 1, 2, 3, 4. Okay, let's do this, right? What's that one thing that you have in mind that, well, because some of you think that's two. Okay, let's take a look. Do we have to predict the result value? Why don't we need to predict the result value?
I mean, I guess the value alone would have an impact on whether the branch visits the computer matters. So or like that doesn't matter. It's just whether you need to go somewhere else or not. It's only that matters for fetching instructions.
Okay, so let's take a look of this code, for example, right? Do we need to predict the value of data I to know the outcome of the branch? Or so regarding the purpose of branch prediction, is the value of data I matter? Does the value of data I matter? Yes? Okay, so, but do we judge the branch result based on the data I or based on if data I is smaller than threshold? Right? So here's the thing, right? We don't care exactly what's in there. We care more about if data I is smaller than the threshold, right? So in this way, do we really need to predict the result value? Okay, so do we need to predict the direction of the branch taken or not taken? Yes, because that's the whole purpose of why we want the branch prediction, right? We want to know if this branch is going to be taken or not taken. How about the third one, the target address? Do we also need to predict that? Do we need to predict the target address? What's the target address? What's the target address of a branch? In branch, what does that mean by a target address? I try to use different way to ask the same question.
I'm not sure that way.
Okay, so now let's go back to this one. So for this pieces of a code, oh, it's pretty. Like for this pieces of a code, like okay, let's take a look of this JE, right? It's written as JEL10. What's the target address? Label 10. Okay, but how do I get the target? How do I get the address of level 10? So the address of level 10 is actually encoded in a way that this level 10 is not being encoded as an absolute address. It's going to be encoded as a relative address. And there is a reason for that. Because if you remember how we compile our code, there are two types of libraries, static library and dynamic linking library. And what does that mean is that in your compiler, in your compiled code, there is a possibility we can dynamically map your library functions or your instructions anywhere in a virtual memory address space. So because of the starting address of the library is not determined before you start running the program, so we cannot really hard code this label as an absolute address because it's going to be changed time by time. However, what we do is that because the relative amount of instructions in between won't change, so what we will do is that we encode as an offset in bytes. Like how many bytes is this instruction away from this instruction that we need to jump from? But what does that mean is that when you want to jump, you have to calculate from what's the current address of this instruction and what's the offset amount from this instruction to L10 and make an addition. So if you want to take the branch, the execution stage, as we previously mentioned, is responsible for calculating the effective address. So if we have to calculate the effective, if we have to calculate the effective address here, not this one, sorry. If we have to calculate the effective address here, right, then it doesn't make any sense for just predicting the direction because you have to wait for here anyway for your target address. Agree? So in this case, we also need to predict the target address. Otherwise, the whole idea of branch prediction won't work. So these are the two things that we have to predict at least. So how do we predict that? So for the target address, as I mentioned, although it cannot be determined at a compile time, however, once I load this code segment into a virtual memory space, the starting address of this code segment will already be determined, and the same location will continue until this program finishes execution. So what does that mean is that this address only need to be calculated once, and that location should be good throughout the whole program runtime. So what does that mean is that the easiest thing to do is that we can keep a cheat sheet in the processor somewhere to keep track of those branch target addresses that we have been visited. And the only thing that we really need to use some wisdom to predict is the taken or not taken. So now you can imagine the cheat sheet in branch prediction is called branch target buffer, which you have each branch PC as a tag and index, and also the target PC as where to jump to as the branch target address. And another thing to do is that, is it going to be taken or not taken? So there are several ways that today we are going to talk about to make a prediction, but let's start with the first one. So the first approach is a 2-bit local predictor. So by 2-bit local predictor, what it means is that we maintain a state machine associated with each entry in a branch target buffer. So what does that mean is that whenever I see I am interfacing this branch, and based on the state here, I would decide if I want to take the branch target PC or not. So that's the idea of the very basic predictor. But now the problem is that how do we transition those states? So the concept of this predictor is that we would make a prediction based on what we previously have experienced regarding this branch. So this is pretty much like some of us were talking about. we keep track of what multiple choice answers that we have experienced. So what you're actually doing is that, first of all, this is a local predictor. So in the terminology of branch predictor, by local, it means that we consider like each branch as a separate entity. Each branch, by branch here, it means the same program counter. For each program counter of the branch, it is considered as a separate entity, and we train the states of each entity separately. And when we train each entity, we use a 2-bit state machine. But this 2-bit state machine is actually, a lot of people, especially the book, they try to complicate things. Consider it as a state machine so that you feel like this is like a computational complexity class. But to be honest, the state machine actually represents, it's just a saturate counter. So what does that mean by a saturate counter? If it's a 2-bit state machine, you can count from 0, 1, 2, and 3, right? And by saturate, it means that if we are at 3, if we want to increment, we are still going to stay at 3. And if we are at 0, if we want to decrement, then we are still going to stay at 0. So this is the concept of saturate counter. And with this saturate counter, what are we going to make the decision is that if we are at the value of 2 and 3, which is more than half of the value can be represented by the saturate counter, we will predict taken. However, if it's 0, 1, then we consider this as not taken. So you can pretty much consider the transition is pretty much if we have seen 2 previous events to be taken, we must predict it to be taken, right? So if in the past there are 2 consecutive takens, it will be considered as taken. So that's the basic idea of that. So let's take a look of how it works. So for example, if I have this pieces of code, which is a while loop, and in fact, as I told you before, there is not really a for loop in assembly language. All machines have to translate, all compiler has to translate a for loop into while loop before we can compile the code. So if you start at 0 and if you have the loop boundary smaller than 1, this is very likely the while loop it will generate. So at the end, the branch condition comes in the case where we want to check if plus I, meaning that I will increment I first and compare it with 10. So saying that when I equal to 0, and now let's assume we are starting at a counter at 2, which is the state of 1, 0. Now, I'm at I equal to 1, and my state is 1, 0. So as the branch predictor, if you look at a branch predictor, should we predict taken or not taken? Taken, right? Because right now we are at state 1, 0, so it's considered as taken. Now, for this branch, is it going to be taken or not taken? For a loop, taken means that we are going back to the loop. Taken or not taken? Taken, right? So we made it right? And it was, as we last mentioned, if it's taken, then we are going to increment the counter. So now we are moving our state to strong taken, which is 1, 1. Okay, so now when I equal to 2, the state is now 1, 1. What's our prediction? What's the actual outcome? Taken. How about I equal to 3? What's the state? 1, 1. What should we predict? Taken. What's the actual outcome? Taken. Okay, so how about 4? Taken. Okay, so to 9, right? It's all taken. How about 10? What's the state right now? Still 1, 1. And what are we going to predict? Taken. Okay, so when I equal to 10, are we going to stay in a loop? So what's the outcome? Not taken. Okay, so look at this, right? With this simple predictor, we can achieve 90% of the accuracy. Are you satisfied? No? I mean, if you can get 90% of the midterm, are you satisfied? No? Okay, not satisfied. Okay. Okay, we will talk about some later, a better one. But okay, now let's take a look at this. If I have a 2-bit local predictor, can you consider what's its effect for these pieces of a code? All right, let's take a look about what you guys think. Okay, so looks like half of you agree with an answer. Some of you don't agree with that. So why don't we just discuss with others and see would that change your mind? All right, so let's take a look. What do you guys see after discussion? Okay, more of you think the answer is D. So how can we thinking like how did you guys think about this problem? Like why is it why most of you now agree it's D? Okay. Mm-hmm. Okay, random guessing, right? And because we have two types of answers, right? It's either like larger than or smaller, right? So 50% of the time, if we do random guessing, right, 50% of the time, we will get this right, right? Okay, how about sorting? Why would sort help?
For sorting, we thought like once the threshold is true once,
Mm-hmm.
everything after will also be true.
Mm-hmm.
So if it gets that right after the threshold, it'll start getting everything right until the end. So that's.
But how about before?
Before it might not, but that depends.
Why not?
Because it would still be random, or not random. Wait, actually no. Before it would always predict not taken after the first one.
Right. So here's the thing, right? So no matter it's taken or not taken because of it's true or false, at least everything, if you store the data, everything before the threshold, they would lead to just one possible branch outcome, right? And everything after reach that threshold, the outcome of the branch is only one possibility, right? So it's either like if it's large taken, then everyone after it's larger than the threshold is going to be taken, right? So what does that mean is that after you store the data, the outcome of this statement becomes really easy to predict because everyone's value out over than the threshold would cause the evaluation to be true. And everyone before would cause the evaluation to be false, right? So your branch predictor can easily predict that. So that's how you can reach like 100% threshold, like branch prediction, right? So this tells you the reason why adding this sort is kind of like an extra work, but we get a lot of performance gain. So if let's see, is it really the case? So this is the code that we had in the first lecture regarding that. And now this is indeed the loop that we have seen before. And this is the code that has been generated in the assembly. And now let's try to check. And I'm going to run this on an Intel processor and see like how does that affect the performance. And as you can see here, okay, so I'm running this with the array size as 128K and with 1,000 queries. So, and if the sorted value is 0, means that we don't sort. And as you can see, okay, let me do this again. It seems like the sampling doesn't give us the right number sometimes. Oh, okay, sorry, no problem. Okay, so, interesting. Am I getting the right code? Wait a minute. Okay, here we go. So this is the demo we have, right? So first of all, without sorting, if you look at the instruction count, without sorting, we do have lower instruction count, right? So theoretically, based on the IC execution time theory, you would think about, okay, this should give us a better performance. However, if you look at the total number of cycles, which help us to calculate the CPI, without being sorted, the CPI is 1. And after you sort, the CPI is only 0.24. Cycle time remains the same, but the execution time is about 4 times difference, right? So a lot of you, after learning about the cache, you will think about, oh, is it has something to do with the cache? But if you think about that theoretically, right? If I'm traversing the loop with the same order, it's actually not going to help. And in fact, if you check the cache miss rate, after the sorting, with the sorting is actually higher because when we sort, we are triggering more memory accesses, which cause more misses. So to be honest, having sorting is making the memory behavior slightly worse. But what really makes a difference is actually if you look at the amount of branch misses, the branch prediction misses, it's reduced by a factor of 100. Right? So it was like somewhere like 34 million, but right now it's just like 300K, right? So you reduce the number of mispredicted branch by a huge amount because you store the data. And that translated to this 4 times speed up. Okay, so this is actually going to tell you how effective is branch in our applications, right? So now, the other problem that we have is that previously we have been talking about memory, and we have been talking about like memory. Right now, the latency of the memory is around like 55 if I access the DRAM, right? And a lot of you now think, oh, okay, once I address the memory, other problems are not that important. And in fact, let me show you, once you address that memory, what's the second most important problem? So let's take a look at this. So the previous benchmark that we have is actually going to give us a good idea about what if we mispredict, right? So think about that. If we set the sorting part aside and we place the measurement of the performance counter just outside the inner loop, what does that mean is that I am counting the same number of instructions and the same amount of operations and see what's the performance difference in cycles, right? That will give us the depth of cycles if a good branch prediction and not having good branch prediction. And we also have the number of mispredict branches at the same time, right? So if I can compare the depth of the numbers of mispredicted branches, then I can actually calculate the average CPI of the mispredicted branch. This would give us an idea about how slow is a mispredicted branch, or say the penalty of waiting for the branch outcome. On the other hand, it would also help us to understand how many pipeline stages do we have, right? So here is how are we going to do with that. So first of all, the same piece of the code would work, right? So now let's run this demo, but I want to run it with more iterations. So what if I do this and I have now this versions of a code, I only place the performance counter outside of the loop itself. So it won't count the overhead of sorting. So with that, now we can find these numbers. So first of all, the amount of branches, they're about the same, right? What really different is the number, the difference in branch mispredictions, right? So an easy thing to do is, here is the number of difference in mispredicted branch. Okay, so let's copy this number. And here is the number of mispredicted branch after we sort data. Right, so this is a diff of misses. Now, this is a different number of cycles that we need to execute the code if it's sorted. And this is the number of cycles that we need if the data is sorted. So now, if we divided that, we can pretty much conclude that's the difference of the CPI of each mispredicted branch. And this gives us the number of 33. So what does that mean? Previously, we mentioned the worst case scenario of cache miss is 55. And for the branch, it's also pretty bad, 33. 33 cycles if you have to wait for the branch outcome to come by. So that's why after we have the design of memory hierarchy, I would say branch is a very critical problem. because it takes 34 cycles to resolve a branch. And this is also the same with other processors as well. So now I'm going to run the same result on an AMD processor. As you can see, this is a 5000 series. And if you take a look of the amount, well, and another thing that is interesting is that different processors, they implement different branch prediction methodologies. So you can see the amount of mispredictions are pretty different among these processors. And now let's take a look of what's the average amount of CPI if I have mispredicted branch. So for each mispredicted branch here, the answer shows it's actually 24. Right? So what does that mean is that if you have a mispredicted branch, the AMD processor would also take 24 cycles to address. Right? And think about this. If I have a branch predictor that can guess 90% answer correctly, right, then I don't have to suffer from this 24 cycles. This would help us to bring the CPI just down to 3.3. Right? So that's why making the branch predictor highly accurate is actually very critical to our performance. Okay, so you know, like this could be more expensive than an L1 cache miss. So that's why this is also an important problem. So we talk about two big predictor can help us address the loop by 90%. But what if my code is not that kind of loop? All right, let's take a look. So, definitely we need some discussion. So why don't you guys discuss with each other and see what you guys think about that? All right, let's take a look. After discussion, more of you think the answer is C. Interesting. So let's take a look of this one. Okay, so let's take a look. Now, I start with 0, right? So now the first branch that we meet is actually branch X. So when I equal to 0, when I meet branch X, what's the state that we currently have associated with branch X? Read it out loud. 0, 0. So predict taken or not taken? Not taken. Okay. So, but when I equal to 0, should it be taken or not taken? Taken based on my comment here, right? So the actual outcome should be taken. So this one is wrong. However, if we, after this taken, are we going to adjust the state associated with X? How are you going to adjust it? Make it 0, 1. Okay, so just keep in mind, next time when we see it, it should be 0, 1. But now, here I'm going to increment I, make it 1. So for branch Y, what's the current state there? 0, 0, and predict not taken, the actual outcome, taken. Okay, so this one also gets wrong. How about now, when I equal to 1, when I come back to branch X, what's the state now? 0, 1, predict taken or not taken? Not taken, right? Because this is a saturated counter. Only when it's greater or equal to 2, we will predict it to be taken. So this one is not taken. What's the actual outcome? Not taken. So when it's not taken, what's the new state? 0, 0. So it will go back to 0, 0, right? Now, when I increment I mid branch Y, what's the state here? 0, 1. Predict taken or not taken? Not taken. The actual outcome? Taken. Now, if we finish the rest of the table, right, you will figure out that for branch X, it will always be vibrating between 0 and 0, 1, which means that we are always going to predict not taken. In half amount of time, we are going to make it right. However, for the branch Y, we are gradually fixing it, and it's always going to predict taken. So we are only going to miss it 3 times, when it's equal to 1, equal to 2, when it's equal to 100, right? So what does that mean is that for this branch, we have an accuracy of 50%. This one have an accuracy of 100%. So what's the average? 75. What was our voting? I don't see anyone vote E, right? Okay, so definitely you need to spend some time figuring out this concept. But here's the thing, the first dynamic branch predictor that we have is called local predictor, predict based on each different branch. But from that, we also see if your structure is not like a loop that is highly regular, we cannot do a very good job, right? So are you satisfied with just 75%? Of course not, right? You guys were not even satisfied with 90%. So how can we deal with that kind of situation? So here comes with another idea. If you just look at branch X and Y, it's hard to predict just one direction, right? However, if you look at the actual outcome, don't you find something regular here? If you just look at the actual outcome, don't you find something regular here? What is that? It's always 3 taken and 1 not taken, right? So what does that mean is that if I could have 4 goals, which branch is it coming from? Right? Previously, we trained predictor based on the local history of the predictor itself. But if I look at just at this line, forget about those. There's actually a pattern here, right? So what does that mean is that can I make a predictor try to capture this kind of pattern? So whenever, for example, I see 1 not taken and 3 taken, I know that's the only case that I should predict not taken. Or when I see 3 taken, I know the next one must be not taken. Right? So for example, if you see in your multiple choice answer question, you see 3 consecutive C's, you will feel like, is the next going to be C? Probably not. That kind of feeling. Right? So this is like a global history. Right? So previously we talked about local, means that we only take care of the X and Y separately. But the global is that let's ignore where is it from, and we consider that they have relevance, right? So like for multiple choice question, you can definitely consider each question has its own probability space, and each one should be independent. But a lot of us, most of the time, we don't believe that's the case. So we would also look at the answers from other priori multiple choice questions. So this is pretty much the idea of that. We should guess based on the answer of other multiple choice questions. So how to make such kind of predictor, right? So the idea is that, okay, if now we are training on the global history, then we don't need to maintain a state machine that's associated with each entry in the branch target buffer. But instead, this is what we are going to do. We are going to maintain a global history register, which keep track of the outcome of the previous branches instruction. So the number of bits is upon the design decision. But right now, let's just see what if I use 4 bits as the history. And if you have 4 bits as your history, how many possible combination of the branch history are you going to see? 16, right? 2 to the 4. So now I'm going to make a state machine with 16 entries, and each entry is mapped to a possible combination of the history. So whenever I want to make a prediction, I consult the branch target buffer for the potential target PC. And then I also consult the current global history. And if this is like 0, 1, 0, 0, then I should go to the 4th entry here. And if it says it's predict taken, then I would take the target address. Otherwise, I would just go to the next instruction, right? So now let's look how would this work. So for this pieces of a code, right? Right now I'm in a case where I equal to 0 and I'm in branch X. And let's assume our global history register is only 3 bits to shorten the time, because the longer the history, the longer the time you need to train. So let's assume the current branch history is just 0, 0, 0, meaning that the 3 previously we think are all not taken. Now, this is the first time we have seen this state. So we consider everyone initialized as 0, 0. So based on that, are we predict taken or not taken? Not taken. What's the actual outcome? Taken. Okay, now, when I increment I equal to 1, when I interface branch Y, what's my global history register now? 0, 0, 1, right? Because the last one is actually a taken, right? So I concatenate this taken here, all right? Now, what's the state in 0, 0, 1? This is my first time seeing this, right? So what's the state of it? My first time seeing this. 0, 0, right? So are we going to be taken or not taken? Not taken. What's the actual outcome of branch Y? Taken. Okay. Now, when I meet X again, what's my current GHR? 0, 1, 1, right? Because I have two takens here. What's the state here? Y is 0, 1. But right now, when I make a branch prediction, I'm basing on the GHR, right? So for this history, have we ever seen this before? So what's the state? 0, 0, right? Are we predict taken or not taken? Not taken. What's the actual outcome? Not taken, okay. But you know this is just like a coincidence, right? Now, when I equal to 2, what's the branch outcome? What's the current GHR? 110, right? Because it's 110. Have we ever seen this before? This pattern before? So what's the value in there? 0, 0. Predict taken or not taken? Are we getting it right or wrong? Wrong, right? So it's taken. Now, when I equal to 2, when I meet branch X, what's the current GHR? 101. What's the current state in there? 0, 0? Okay, have we seen this? So what's the prediction? Not taken. What's the outcome? Taken. Okay, at this point, you start to feel like, wait, is it going to work? Right? It's horrible. Right? Now, let's try it one more time. I equal to 3, branch Y. What's the current GHR? 0, 1, 1, right? 0, 1, 1, right? Have we ever seen 0, 1, 1 before? Okay, what's the value in there? So previously 0, 1, 1 is 0, 0, and it's not taken. So what's the state? 0, 0, right? So what's the prediction? Not taken, but what's the actual outcome? It's actually taken.
Comeback time.
Comeback time, yes. Okay. Right, so see, this doesn't work out, right? Now, how about this? What's our current GHR? 111. Have we ever seen this before? What's the value? 0, 0. Predict taken or not taken? Not taken. What's the actual outcome? Not taken? Okay, we guessed it right, right? But so far, how many? 1, 2, 3, 4, 5, 6, 7. We only guessed 2 right, which is even worse, right? Your feeling is like, is this going to work? Seriously? Right? Just be patient, right? I'm a teacher, so I'm really patient, right? This is like my feeling every time when I educate students. All right, so for Y, let's do it again. What's the current GHR? 110. What's the state? What should be the state in there? So previously, have we seen 110 before? And what was the outcome? Taken. So what's the value there now? 0, 1. Are we predict taken or not taken? Still not taken. What's the actual outcome? Taken. We still got it wrong, but things are changing, right? That's my feeling every time when I'm teaching a concept. Now, when I equal to 4, X, what's the current GHR? 101. Have we ever seen 101 before? Okay, so what would that change our state to? 0, 1. What's our prediction? Not taken. What's the actual outcome now? Taken. We still got it wrong, but something is starting to change. Now, when I equal to 5 at branch Y, what's the GHR now? 0, 1, 1. Have we ever seen 0, 1, 1 before?
Yes.
Yes. So what's the state should be there? 0, 1. Predict taken or not taken? What's the actual outcome? Oh no, right? Now, when I equal to 5, X, what's the current GHR? 111. What's the state in there? 0, right? Because the last time we saw 111 is 0, right? So this one still stay at 0, predict not taken, and the actual outcome is still not taken, right? So this one we always guess it right. Okay, how about I equal to 6 at branch X, Y? What's the current GHR? 110. Have we ever seen 110 before? Okay, what should be the state in there now? 10? Predict taken or not taken? What's the actual outcome? Oh, things are starting to change, right? Now, when I equal to 6 when we meet X, what's the current GHR? 101. What's the state in 101? 10, right? Because previously it was here, right? And it was 01, but because it's true, so increment it, right? What's the prediction? Taken. What's the actual outcome? Taken. Next. What's the current GHR? 011. What's the value in 011? 10, right? Because the last time it was taken, so it's incremented by 1. Predict taken or not taken? What's the actual outcome? Taken. Woohoo, we got it right again. How about this one? What's the current GHR? What's the value in there? 0, not taken. Actual outcome? Not taken. Next one. What's the current GHR? 110. What's the current value in 110? 11. What's the prediction? Taken. What's the actual outcome? Okay, so if you keep going, if we 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 keep going, the magic is that we are going to have 100% hit rate after a certain point, right? So now, you know there are global predictor and local predictors. What's the strength of weakness? All right, let's take a look. Okay, so most of you guess the answer is C. So why don't you guys discuss with the two that you have in mind, compare against the others two? All right, let's take a look. So after discussion, okay, B or C. So for the first one, is global going to be better than a local? Is global going to be better than a local? Yes? Why? So how accurate is a local predictor on this branch? How accurate is this one for the local predictor? How accurate is that for a local predictor? No. Why it was 75? Why was it 75? Okay, so for this branch, how accurate, this particular branch, how accurate is a local predictor? How many times are you going to guess it wrong? Every 1 out of 10, right? You're only going to guess it wrong when mod 10 is equal to 0, right? So 90% of the time. How about this? Almost 100% of the time, right? So how about a global? Can 4-bit capture this? No, right? Because it's actually 10 bits. You need a 10-bit history to capture that exception. So what does that mean is that there is no difference between these two, right? How about this one? Is global going to be a better job or local going to be a better job? They're about the same, and based on the time we need to train the global predictor, I would say local is probably slightly going to be better. How about this one? Who is doing a better job? Okay, so this one is pretty similar to the situation that we have seen, right? If I mod equal to 2, right? So because this, for this case, right, we are just like go between 1 and 2, right? So for this case, it's pretty much like a case of I mod 2. So this one, and given we have 4-bit history, so we are capturing this very well, right? So global is doing a better job on this one, right? How about the last one? Why? Okay, so because this one is really random, right? You might argue local doesn't do a better job on this. True. But if you have something random in your global history, it will pollute the training of the global predictor. So what does that mean is that local is probably going to do a better job here, right? So what does that mean is that there are pieces of a code that local can outperform. There are pieces of code that global can perform better. Both of them has their drawback in proficiency. So the modern processor, they incorporate several different types of design. One of the most common one is called like tournament predictor. So the basic idea of tournament predictor is that associated with each branch, I also have a state machine associated with it. But this state machine is not something that I would use to predict the outcome of the branch. Instead, this is a predictor that predicts which branch predictor is going to give you a better prediction. There are a lot of predictions. So it means that in my design, I can have a local predictor and a global predictor. They can make predictions simultaneously. However, based on who gets it right the last time, I would give higher confidence of that predictor to trust its result. So for some branches, like the ones that are highly stable, I would trust the local one. But for the ones that are probably not as stable, I can, from my perspective, I can probably rely on the global history predictor to give us a better result. Right, so that's the concept of tournament predictor. It's basically giving you another layer of prediction, telling you, making us, helping us on a decision, right? And another predictor that is pretty popular nowadays is called perceptron. So if you have some idea about neural network, you probably would get a feeling about what perceptron is about. And if you pay attention to that, perceptron is a paper published in 2001. So that proves, long time ago, I've been talking about like neural networks was once popular in early 21st century or before that. And in fact, computer architects, we are one of the first group of people who try to incorporate neural networks in solving our problem. Because branch prediction is basically a classification problem where we use the previous history to predict what's going on. So we can actually mapping the branch prediction to a neural network problem is that the input is just a set of branch outcome from the history. And if the branch is taken, we put it as a value. If the branch is not taken, we predict it as another value, right? And based on the value, we predict the outcome or not. So, and then we can formulate a linear function that take the inputs and take the dot product, make the matrix vector multiplication to calculate the final sum. And there is also a training algorithm being proposed, and pretty much it's also some kind of hybrid predictor in a way that the perceptron predictor, when we train the weights, right? If you can think about the concept of these weights, it's basically giving confidence label to each bit of the history, right? So it means that we should trust this bit of history more or less. So that's actually the meaning of the weights here. So for example, like this particular branch, what happened to the perceptron is that we can give lower confidence level to this branch because it's pretty random. It's hard to predict. So in this way, it will simulate the effect of a local predictor. However, if the branch also consider this is a highly confident branch, then it will be equivalent to a global predictor. So that's why we say perceptron is also some sort of hybrid predictor. And in fact, perceptron is also one of the predictor that has been using in AMD processor and Samsung's mobile phone processors. So it's indeed in use nowadays in your processor. So all the branch prediction methodology that I introduced today, they have been once or still in use. So they are pretty useful. But the big takeaway here is that all modern processors, they all have branch predictors. So based on what you have learned from this lecture, you should try to make your data more better aligned to make it more, or change your code, change the way how you write your else statement to make your code easier to predict. So that's the takeaway of this lecture. And before you leave the classroom, we have a reading quiz due tomorrow, and we have an assignment 3 due this weekend. And if you want to take the second chance midterm, which is not mandatory, but if you want to do it, here are the dates available, and don't forget to make a reservation. Other than that, enjoy the rest of your day. I will see you tomorrow.